Right, so welcome back to the lecture. Lecture number 2. We're going to talk about fields today. And as I shown in the video earlier, the field is actually like a slope. Right? It's a slope. So it's actually a region of space in which an object will experience a force. Right? A gravitational field is a space where a mass will experience a force. Okay? Of course, and then this changes. An electric field will be a space where a charge experiences a force. Right? Your force lecturer should have done this for you. Okay? So the strength of the field we denote by the alphabet G, small g. Right? And it's also sometimes called the acceleration due to gravity. The strengths of the field can be represented by lines of force. What are they? These are the lines of force. So the closer they are, if you look at my mouse, right, the closer they are, the stronger the field. The further away they are, the weaker the field. Okay. So if I give you an example of point A, right, point A. So this you need to write down, point A and point B. Which one has a stronger gravitational field? Which point has a stronger gravitational field? A. Right? The dotted lines that you see on the circle are called equipotential lines. I'll get to them later on in part 5. But this is a good point to start remembering them. They are called equipotential lines. What are they? Well, it's on the part on potential later on. Okay, this is the video I showed you. Gravitational field near the Earth, right? We walk around Singapore, walk around the surface of the Earth. We say that G is 9.81. Right? Is 9.81 everywhere? It means that the field is always in the same direction and of the same magnitude. Right? You see that the lines are equally spaced apart. So you will learn more about fields in electric fields, but this is a good time to start thinking about them. Right? Field lines and force lines. Right? These are the force lines. Okay? Now definition, this is important. Right? The gravitational field at a point, the gravitational field strength at a point in a gravitational field is defined as the force per unit mass. Force per unit mass. Literally, you know that weight is equal to m times g, right? You have learned in secondary school that W is equal to m times g. What this definition is doing is just taking m and dividing throughout. So you say G is W over m. Right? So it's force per unit mass. Okay? Simply this. Right? Nothing special. But what comes out is different because you know that F actually depends on R in the previous lesson. F equals to G m1 m2 over r squared. G m over r squared. Right? You can actually rearrange, right, to get this. G is given by Gm over r squared. Okay? Which is what you need to copy. Okay, and sometimes we give the negative sign. Actually, most of the time we give the negative sign. Okay? But the negative sign means it is attractive in nature because both force and fields are vectors. Okay, we will see it in the next example very clearly. How do you add forces or fields together? Okay, very important. This example that's coming is super important. Right? So example 6, you have two masses, right? 800 and 600 separated by 0.25 kg, 0.25 meters, right? And the distance of x to m2 and x to m1 are respectively shown in diagram. So you can say that they individually, right, M2 provides a gravitational field on X on G2, M1 provides a gravitational field on X G1. You are asked to find, right, what is the field and especially what is the force eventually, yeah? So you can first find the field and then multiply in the mass of an object at X to find the force. Okay. So they ask for what is the force, 300 kg you experience, but before that they ask you what's a gravitational field. Okay. So gravitational field at X, right, is this part. This is not in your notes. I want you to put a star and say must sum by vectors. All right, sum by vectors means you must add it as if it's two velocities and you find the final velocity. Okay. So these are two G fields, G1, G2, add together you get a final G. But you must sum it by vector. So vectorial addition means what? Parallelogram, right? Parallelogram, or you draw some triangles. Okay. So you look at a diagram given to you that I printed out. I give you half the answer. Right? This is given to you. But what is missing is this diagram. Can you add it to the diagram of the picture in your notes? Right, the resultant G field in this diagram given to you. Right, add it in that diagram. So you remember how to find the resultant force. Right? If you are not careful, you will just add G1 plus G2. You forget there's a vector. Right? But here we are very lucky, right? Because G1 and G2 are perpendicular to each other. Am I right? That's why you can use Pythagoras theorem. Am I right? If they are not perpendicular, then you must use some kind of vector addition, right? By resolving one component to the other, and add them together and find it, right? Your vectors, the teacher should have taught you that. But let's start with the easier one. Huh? You may get the other ones later on. Okay. So is this the end? They ask you to find the resultant field. Is this the end? As I said, gravitational field, like force, is a vector. A vector has both magnitude and So have you found the direction yet? No. That's why we have also this angle theta here. You must be clear. Right? You must mark it out in the diagram. What is the angle theta you're trying to find? Before you find it, I have many students solving for theta, but they did not mark theta on the diagram. Then I don't know what they are doing. How do I give credit the marks? Right? In Cambridge, it's a cold winter night when they mark your, when they mark your scripts. It's Christmas time. Their children don't come and visit them. They are grumpy. Then you never put in theta. You think they want to give you the points they're learning, right? So you want to mark in angle theta, right? Be nice to them. Make it clear that you know. There you go. So angle theta, I use tangent. It looks very difficult, but it's not at all. It's not at all. You have already solved the values individually earlier on, right? And you'll find it. It looks scary, but it's not. Right? You can in fact just use what you have on the left-hand side of the You don't need to copy this answer because you can solve it already, right? With the diagram and you have the value of G1 and G2, you can solve it indirectly. You don't even need to do this step. Okay? But if you want to copy, go ahead. It's easier for you. Alright, so I found both the angle and the magnitude of the gravitational field. Then the question asks you, what is the force? If you have the G, force equals to mg, right? So you found the G, can you find force? Yeah, very easy, right? Just multiply by 300. Okay. Any questions at this point in time? Anyone? No one? Right, so this example, please mark a star. Right, a lot of our students later on, about 20-30% will forget it's a vector. Right, and later on got caught by this, and it's not nice. Right? It's not nice. So, I mean, to conclude, the force is just m times g, like I said. It's on the same page. It's the same example. Right? It's the same example. You just need space below. And just say that I take the g value of g, multiply by 300, I get this answer. And you put it to an angle to g2. That's it. Okay. So be very careful. This question asks for force. Okay. So some students may come to me later and ask, sir, can I solve for the forces first? I solve for force of m1 on 300 kg and then m2 on 300 kg and add together. Yes, you can. It's the same thing. It's whether you add the fields together, then you multiply by m, or you multiply by n and add them together vectorially. It's the same thing. Okay. But I like adding g together first because then I have one. I can multiply by 300 one less time. Lazy at that. Okay. Right. Next. The next question is actually pretty interesting, right? The next question is actually pretty interesting. They ask you to find the mass of the Earth. Have you ever wondered as a child, right? How do people find the mass of the Earth? You can't actually put the Earth on a weighing scale, right? Can you? If you can, then you are a superhero. Right? You're Thanos or something. But you can't, right? So how do you then find the mass of the Earth? With gravitation now you can, right? How do you do it? Right? We know the radius of the Earth, assuming we know the gravitational field strength. We've already found gravitational field strength through kinematics, right? Which we'll show in example 3.2. All we have to do is take the equation for gravitational field, rearrange for that of mass, substitute in the radius, substitute in the value of 9.81. We find that the mass of Earth is 6 times 10 to the power 24. That's actually pretty easy. Of course, I'm taking g to be 9.8 now, not 9.81. Just because the order, the magnitude is what we are more concerned with. Okay? So the harder question is actually what is the radius of the Earth, right? How do you measure it? How did the ancient scientists measure the radius of the Earth? They walk around the Earth, right? Take a measuring tape, they walk around the Earth. No, right? Cannot. So you must think about how to do it. Go back and Google. It's very interesting to find out how the ancients have done it. Anyway, next example, they ask you what's the density of Earth. So boring, right? You know the mass, you know the volume, you know the radius, you can guess the density, right? Do you know I got this equation? Oh, this is what you need to show, right? Density is mass over volume. Okay? Mass from the previous example number 7, right, you found to be g r squared over big gravitational field constant, gravitation constant. Volume 4 over 3 pi r cubed. Cancel out the parts, you get this. So easy, shown, huh? Easy peasy. But the showing is not the part that is the most important science. The important part is this. Is this G and this R. Because you realize that 3, 4 pi, and capital G are all constants. Right? So, in fact, if you rearrange the whole thing, you can give G with respect to R and density. Right? You can find the density, the gravitational field strength on any planet, right, by the density of the planet, the mean density of the planet, and the radius. Okay? So there are a few questions like that plays with this idea. That's why I need to introduce this now. Okay? Moving on. How do you determine G? We have done this already. In your student activity, we showed you the light gate. We have also done this in your kinematics tutorial, question number 4. Yes, my memory is good like that. Actually, I'm not sure, I'm just guessing. But most of you will remember. Have you watched the show? Okay, never mind. We are recording, so. Alright, so this one is I'm just going to go through. What happens is that you have an electromagnet and a ball bearing. Once you turn off the ball bearing, the timing starts from 0. It falls, it passes to the first light gate, measure T1, passes to the second light gate, measure TB, TATB. Then you use these equations, which you have already done in your kinematics tutorial, right? And your student activity, you actually get this answer, right? You can find G by measuring H, knowing TB and then TA, right? I'm just going to breeze through it because you should already know. Just reiterate this to you. Right. Next is a very interesting part of physics. What is the value of G, right, depending on height and depth? We know height because G, gravitational field strength, G equals to Gm over r squared. So the further you are away from the center of Earth, the lesser the G. Correct? Do you agree? Does it mean that the closer you are to the center of Earth, the higher the value of G? Right? If I did not do the next part for you, that is what you will go away thinking, right? But you had learned, if you look at example 8 and 7, we build up to this. So part A is what I said just now. This is true. Okay. Further away you are, the lesser the magnitude of gravitational field strength. Right? You know, please join the curve. Right? The hard part is actually part B, when you are within the Earth. Right? When you're within the Earth. Okay, this one is just copying one equation and one graph. Just sketch very briefly, don't need to be pretty. Right? Why do we not draw, but one of the points here, why do we not draw within R, where R is the radius of the Earth? So notice that we always use small r as a variable and big R as a value. R is a fixed value, capital R is a fixed value of the radius of the Earth. Why do we not draw inside? Because inside, this equation does not hold. Right? So this point is important. Within the Earth's surface, this equation does not hold. We must do the next part, which is, okay, this is not so important. Obvious. It's obvious enough, mathematically it's obvious enough. So let's do the next part. Below the Earth's surface, right, the first thing that you must know is this theory, that the gravitational field, so this, the black line is the surface of the Earth. So now you're inside by a certain radius already. The first thing you must know is that the gravitational field strength, listen carefully, at point P within the Earth, depends on only the mass within that radius. Do you hear me? That means the mass on the outer side, there's a mathematical theorem that allows you to arrive at that conclusion. I'm not going to go through that theorem for you. You can go and ask your math teachers. But I'm going to tell you that the gravitational field at point P, a certain radius from the center of Earth, but not larger than the radius of the Earth itself, depends only on the mass of the radius within that radius. So notice this Gm, this m, is not the mass of the Earth anymore. It's the portion of the mass within the radius. Okay? Oh. Say until my lips are dry. So what is the mass? The mass is 4 pi r, r being a variable, 4 pi r cubed times density. Quite loud now. Suddenly everybody's very quiet. Which no the graph you see here, if you draw the first graph on this point is okay. Why? Because I'm going to show you that both of them link up together. And it's okay. Just give me some feedback. But right. So this assumes uniform Earth density. Right. Let's write this down. Of course, we know the Earth is not equal density, right? Earth has an iron core, and there's a molten area around it. Then there's a crust, and so on and so forth. The density will not be the same. But assuming that, what will we have, right? We'll have this, we will have G to be equal to 4 over 3 constant density times R. Which means within the radius of the Earth, gravitational field strength looks like this. Isn't that interesting? Right? Looks like this. Let's say it's the combining the two. Okay, so you have this. So you combine the two. If you combine the two together, you get this. Not a problem. I show you again. The first part A, I showed you the gravitational field strength outside of the Earth. This part, I show you the gravitational field strength within the Earth. Right? So if you actually combine the two, you actually get something like this. Within is G proportional to R, externally is G proportional to 1 over R squared. So if you drew it on in the axis I gave to you, you can just combine them together, it's fine. Okay? Time flies. Or am I speaking too slowly? A bit too slowly? Right? Maybe I should go faster. Okay, but the beautiful thing is this. Theoretically, what's the fastest way to get from Singapore to New York? New York is roughly about opposite of the Earth from Singapore. Theoretically, the fastest way is to teleport, right? But let's say that does not happen. Physically, how do you do it? The fastest way is a straight line, right? So it's through the center of Earth. And you can do it theoretically. You can drill a hole through Earth. Literally, let's say I need to have my friend at New York receive a parcel from DHL, I call it Caleb HL, right? And I can drop the parcel over that hole. That hole will through center of Earth and come out from the surface of New York, right, at the other side, and you can just catch it like that. Okay, that's the theory. But the problem is that people have tried drilling a hole into Earth. The deepest hole I think they did was in Russia. I mean, Russians are extreme, right? So they will try, let's dig the biggest hole. Right? And they were like, but they couldn't get very deep, right? Even the Russians could only get to a certain height before the pressure crushed their machinery, right? So is this an impossible idea? It's not, because I think the Japanese are thinking of, instead of slicing through the center of Earth, they are thinking of slicing like from here, just a very small portion, right? And that G will also allow you to accelerate something through it using the gravitational field of the Earth itself. That means it's free energy, It's not free, it's free transportation. You just drop, you'll fall, accelerate. Once it goes to the other side, you'll flip in direction and then go out. Right? So I think there was some movie that did that. There was some movie where they were transporting, then halfway through, once they go past the midpoint, they will flip in direction. There was a movie, I forgot what's the name. Total Recall, is it? Okay, Total Recall. That was the show. That's right. Physics, right? Physics applied in Total Recall, and that one was correct physics to some degree. Okay. Anyway, fun stuff over. Right. So now, let's try example 9. Assuming uniform density of Earth with radius r, what is the gravitational field strength at 1, r above the surface of the, at a height r above Earth's surface, that means it's 2r distance, and a depth half r below Earth's surface, that means half r from the center of Earth. So, first one is easy. 2r is just, the g on the surface is 9.81. You double the r. Because gravitational field strength is proportional to 1 over r squared. If you double the r, you quarter the g, you get 2.45. Oops. Okay. You double the r, you quarter the g, you get 2.45. For the portion within the Earth, if you halve the radius, right? Because the within Earth, g is proportional to r. If you halve the radius, you halve the g. Not a problem. So it is simple applications of g. It's actually quite cool. Those of you who are a bit more geeky like me, or just interested or inspired, right? You can go read it up. There's some, you can read out about trains that pass through within the surface of Earth and how they actually try to engineer it. The science is quite amazing. I think I've calculated it takes roughly a few hours only to get from Singapore to New York. It's like literally 1 or 2 hours. I forgot the exact number, but it's really fast. Assuming you don't burn up, assuming no air friction and all that. But usually, if there's air friction, right? If you drop a parcel here in Singapore, you'll never reach New York. You know why? You'll fall through. Then you will not be close enough to the surface. The surface cannot catch it. Then you will just oscillate forever. It's like until you come to a stop, dead center of Earth. Then you're stuck, which is sad. Because you've been experiencing weightlessness and yet you cannot go anywhere, right? Oh my god. Okay, moving on. Example 3.4 is super scary. The physics is, however, very easy. The scariness is with the physics. It's the math, right? They ask you to prove that G is approximately that. It's approximately this when H is bigger than R, and approximately this when T is much smaller than R. Okay. That means it's just for a slight distance above Earth's surface and a slight distance below Earth's surface. They want you to prove these things. So this is a mathematical question. All right, it's a mathematical question. I'm not going to keep you. It's a mathematical question. So I'm just going to flash to you and show you where the physics is. The physics is like this. This is the physics, right? Where my cursor is moving is the physics. Stuck in what you need to do. This part, this whole long chain is just mathematics. Right? You can do this easily if your mathematics skills is good. This is binomial expansion, right? I've given you the understanding, right? Because previously they don't have this. I gave it in the note that bracket 1 plus x power n is possibly 1 plus nx when x is possibly 0. I'll give it to you. It's just math. Huh? Oh, glorious math. Oh my god. More math. The harder one is this one. When your radius is slightly smaller than the radius of Earth, you have to remember that the mass here depends on intensity and this radius. So you substitute in, you will get this equation. Right, so this is the slightly harder one. You can highlight this, which is what you've learned in part B, 3.3 part B on page 11. You get this. All right. So mathematically it's difficult, but scientifically it's super easy. Okay? Scientifically it's super easy. Physics is easy for me. I just had to say that, right? Sorry. Right, I've covered the first two, which is force and field. Okay, force and field. I'm now going to teach you gravitational potential energy in this part. So it makes sense now to take a break in the recording.